Welcome to the second part of our Chapter 4 on nuclear chemistry. Here we're going to be dealing with nuclear reactions. So it's going to be it's similar to when we write our chemical reactions in the next chapter. So hopefully you're paying close attention to all of the symbols and details, because what we're doing here for the nuclear type is going to apply for the electron-based reactions in the following chapters. So back in 4.1, where we talked about natural radioactivity and we looked at symbols for the different types of radioactive decay, now we'll be using those symbols as part of an overall reaction equation to show nuclear reactions in detail. Alright, we've already talked about the alpha particle, so let's talk a little bit more about the process of alpha decay. When a radioactive nucleus emits an alpha particle, a new nucleus forms that has, well, obviously because the alpha particle has a mass number of 4 and a charge of 2, we're going to have now a mass number that's 4 less than our starting nucleus and an atomic number that is 2 less from our starting nucleus. So we see in the bottom right there, uranium-238 is decaying into thorium-234, and the alpha particles. So thorium is element 90, 2 less than uranium, element 92, and this particular isotope of thorium is thorium-234, which is 4 less than the mass of the uranium-238 isotope. So this is really neat. It gets to test your symbol writing skills and your math balancing skills. And if you notice, the total number of the mass number and atomic number on the left side equals the total number of the mass numbers and atomic numbers on the right side. The 238, 92 on the left for uranium equals the 234 plus 4, 238 on the right side, and the 90 plus 2, 92 on the right side for the atomic number. So in a complete balanced nuclear equation, we should see that. We should see that the sum of the mass numbers of the unstable isotope and the products are equal, and the sum of the atomic numbers of the unstable isotope and the products are equal. So here we see in a different example, californium-251 decays by alpha emission to give curium-247 plus helium-4. So 251 on the left for the mass number equals 247 plus 4 for a total of 251 on the right. And then 98 on the left for the atomic number equals 96 plus 2 on the right. 98 is a total for the products. So this gives you a way to double check your work, make sure that you've done careful at least calculation for the mass number and the atomic number. Getting those element symbols right hopefully isn't too much trouble now that we have our handle on the periodic table from back in chapter 3. So as we've done before, we're going to have a strategy here for completing a nuclear equation. And so first up is to write the incomplete nuclear equation. That's based on how much information we're given in the problem. And then number 2, we can determine the missing mass number by looking at the left and right sides of our nuclear reaction to see what we need to balance those out. Likewise, for the atomic number, we look at the total atomic number on the left side and the atomic number on the right side and see what's missing and where to get our total atomic number to balance, just like we did in step 2 with the mass number. Finally, number 4, now that we know the atomic numbers, we can find the symbol of any new or missing nucleus. And number 5, we can complete that nuclear equation and check to make sure that the mass numbers, the atomic numbers, and all the symbols are correct. Okay, so let's work an example problem together. The equation for alpha decay here, we want the equation for alpha decay of radon-222. So radon-222 has an atomic number of 86. That's element 86 is radon. Radon is the element with 86 protons in its nucleus. And so that's going to give some new isotope plus the alpha particle, the helium nucleus there with the mass number of 4 and the atomic number of 2. So if we want to find the missing mass number, well, we know that on the left our total mass number is 222 from that radon-222 isotope. On the right hand side, we know that we already have a mass number of 4 from the alpha particle, so we need to know what 222 minus 4 is, and in this case it's 218. For step 3, we know that the total atomic number rather on the left-hand side is 86, and on the right-hand side we know that we have an atomic number of 2 from the alpha particle, so we need to know what 86 minus 2 is, and we find that to be 84. So now we're ready for step 4. If we're looking for element 84, we scan the periodic table and we see that that is polonium. So now we have the missing mass number, the missing atomic number, and the symbol, and we're ready to move on to step 5. Okay, so finally in step 5, we're completing everything now. We have all the key missing details, and so we're taking our radon 222 and showing that arrow to say that it yields, after radioactive decay, polonium 218 plus the helium nucleus, the alpha particle. So there we have it. Everything checks out. The symbols are right. The math is good. We've done it. So hopefully you'll be able to do this again when it comes to the exam, or at least practice it with the homework set first. Alright, so now that we have our handle on alpha decay, let's look at beta decay. So as a reminder, in beta decay, a beta particle is an electron emitted from the nucleus, and it forms when a neutron in the nucleus breaks down into a proton and an electron. So if we're thinking about an instance of this, we see here carbon-14 forming nitrogen-14. Since the proton and the neutron have roughly the same mass, we don't expect a change in mass number, but we do expect a change in atomic number, and in this case, because that neutron is converting into a proton, we expect the atomic number to go up. So if we compare on the left-hand side, we have carbon-14, mass number 14, atomic number 6. On the right-hand side, we have, therefore, a mass number of 14, because there's a 0 for the mass number of a beta particle. But when we look at the atomic numbers, remember, it's a -1 for the beta particle, so we actually need to go up 1 and have 7 here for the the atomic number of our product, so that 7 plus a -1 gives us a 6, just like the carbon atomic number that we started with. Alright, so just like we did for the alpha decay, let's look at applying that process to determining the complete and correct nuclear reaction for an equation for a beta emitter. So if we consider the decay of potassium-42, which is a beta emitter, we take step 1, and just like we did for the alpha emitter before, now we're looking at a beta decay process. So it's going to be our potassium-42, element 19, mass number 42, goes to some unknown product, and the beta particle, the 0 - 1e electron. For step 2, we're looking at the mass numbers, and since the mass number for a beta particle is 0, we're going to have the same mass number, so it's still going to be 42 on the right-hand side for our unknown element. To find the atomic number, well, potassium is element 19. In the case of our product, we know it's going to be 1 higher, because the atomic number for the beta particle is a -1, so we must be 1 more, and so if we add 1 to 19, we get 20. And then if we look at our periodic table, we see the element with 20 protons is element 20, calcium. Now we're ready for our final step. So here we go. In order to complete the nuclear reaction, we just plug in the element symbol for calcium. Its mass number, just like the mass number for the isotope of potassium that underwent beta decay, is still 42, and the atomic number is 20, such that on the left-hand side we have 42 and 19 for the potassium isotope. On the right-hand side, 42 plus 0 gives us a total of 42. 20 plus a -1 gives us a total of 19. We have a complete, correct, balanced nuclear equation for a beta emitter now. Alright, so now let's check and see how you do on your own. Your challenge here for this learning check is to write the nuclear equation for the beta decay of cobalt-60. So it's very similar to what we just did. Now you're just starting with a different isotope, and obviously ending with a different isotope, but the rest of the process is the same approach. So pause the video now, take your time, do this thoroughly and correctly, and we'll check in with you when you start back up. Okay, hopefully you were able to fly through those first 4 steps. Write the incomplete equation. So cobalt-60, a beta emitter, Therefore, on the product side, you're going to have some unknown isotope and the 0, -1 E symbol for the beta particle, just like we did before. Determine the missing mass number. Well, just like the example we worked together, since the beta particle has essentially no mass, the mass number doesn't change, so it'll still be 60. To determine the atomic number, we have to look at the fact that the beta emitter, the beta particle itself, has a -1 for the atomic number, and therefore we need to be 1 higher than cobalt, which is element 27. Therefore, we're now at element 28. And if we look at the periodic table to find a symbol for element 28, we should see that it is nickel. So the process may have taken some time, but hopefully it was comfortable based on the one that we worked together there for the potassium beta emitter. Okay, now finally it's just putting all those different pieces together. So on the left-hand side we have our cobalt 60 isotope that's going to be the unstable nucleus that will decay. On the right-hand side we have our beta particle, 0, -1 E, and our nickel 60 isotope. So if we add the left and right sides, we should see 60 for the mass number of the cobalt, 60 plus 0, 60 on the right-hand side as well. 27 is our atomic number on the left side. 28 plus a -1 gives 27 on the right side. So hopefully this process, even if it took a little time, if it's your first time doing it, hopefully it was fairly easy to do and you're comfortable with it. If that's not the case, please do try additional practice. Practice some additional alpha decay as well as beta decay examples from the end of the text, the end of the chapter anyway, and the homework set, and certainly reach out to me if I can be of any assistance. Okay, so now we're ready to talk about equations for another decay process, positron emission this time. If you remember from last time, we defined a positron as an anti-electron, roughly the same mass and symbol as an electron, but with a +1 instead of a -1 for its charge number. So this happens by a proton converting into a neutron and a positron. So because the proton and neutron have essentially the same mass number, we expect no change in the mass number. But because the positron was the proton's defining characteristic when the proton's converted into a neutron, now even though our mass number hasn't changed, our atomic number should decrease by 1. And we see here an example of manganese 49 decaying into chromium 49 plus that positron that's emitted. Finally, the last main type of radioactive decay that we'll focus on in the course is gamma radiation. So in the case of a gamma decay, this is the easiest one to write as a nuclear reaction because gamma radiation has no mass and no charge. So it's just energy emitted from an unstable nucleus. The nucleus relaxes down to the stable state, and it's still the same isotope of the same element. So if we look at the example here, we have technetium 99. The little M there after the 99 indicates that it's a metastable nucleus, so it's not truly stable. It does have extra energy that it wants to relax, to emit in order to go back to a more stable state. And so that 99M over 43 for technetium, the element symbol Tc for technetium, goes to just a plain old 99, no more M here in the product. Still element 43 plus that gamma, either just the plain Greek gamma symbol, or as we see here, the gamma with the 0 for the mass and the 0 for the charge number. So this is your best friend. This one's pretty easy to pick out. That M gives it away on the left, and then pretty much the M on the left gets eliminated, and you add in the beta or the gamma particle, rather gamma emission, not a particle, but rather a high energy photon beam of light, and it has 0 mass and 0 charge. Here's a nice visual to show you the different types of radiation sources and the radiation in the new nucleus that we're looking for. So in the case of an alpha emitter, our radiation is that alpha nucleus with a mass of 4 and a charge of 2, and you get a new element as our co-product, an element that's 2 less in terms of the atomic number and 4 less in terms of the mass number. For a beta emitter, we see our beta particle there, our high-speed electron that's shot out of the nucleus, and our new element that's formed along with that is going to have the same mass number because the beta particle has essentially no mass, but the atomic number will have to be 1 greater because the electron has a -1 there, and ultimately it came from a neutron converting into a proton. Our third one down there, positron emitter, has the positron, which is the anti-electron, so same mass, opposite charge as our beta emitter, and a new element here that's going to have the same mass number, just like with the beta emission, but now the atomic number is going to decrease by 1 because the positron came from a proton converting into a neutron. Finally, for a gamma emitter, we're going to have the gamma symbol, and with or without the zeros, I'll accept it either way. And then finally, the stable nucleus of the same element. So on the left-hand side in a nuclear equation for gamma, we should have a little m with the mass number to denote it as metastable, and then on the right side, we just no longer have the m, the mass number is the same, the atomic number is the same. So hopefully this summarizes it nicely, and hopefully you've been able to follow along quite easily. We tend to focus on the major types of radiation, and they tend to be pretty straightforward, I hope. Now, so far we've been looking at what's produced by the natural decay of a radioactive isotope. We can also think about how those radioactive isotopes get made in the first place. So if we have a stable nucleus of a given element, we can bombard it with a small particle, like in this case we see an alpha particle here, to make a new and different substance. And this is, if we change the element's identity, this is called transmutation. So in this case, if you look at the sort of visual of the nuclei, we have an alpha particle hitting a boron 5 isotope, the nucleus of a boron 5 isotope, which is a stable nucleus. Both boron 10 rather, and boron 11 are stable nuclei. But when we get the alpha particle to bombard it, we can make nitrogen 13, which is a radioactive isotope of nitrogen, and we'll also have a neutron left over. So here's a case where we're really looking at 2 reactives and 2 products, instead of what we've done so far has just been a single active radioactive nucleus decaying. Now we have a stable nucleus that we're hitting with an alpha particle to make a new radioactive nucleus, and then in this case also a neutron, and that radioactive nucleus, the nitrogen 13, obviously will go on to do its own radioactive decay. So just to summarize, when we have that stable non-radioactive boron 10 nucleus and we bombard it with an alpha particle, we can produce radioactive nitrogen 13 and a neutron as well as our co-product, just to make the mass numbers balance out there properly. Alright, so let's follow up with a learning check here. What radioactive isotope is produced when a neutron bombards cobalt-59 and emits an alpha particle? So make sure to use your stepwise approach, or another approach if you have one that works for you all the time. You don't have to use the one in our text, but go ahead and pause the video if you need some additional time. When we start back up, we'll take a look and see how you did. Okay, so here we have the incomplete nuclear equation. So we have that neutron, lowercase n with a superscript 1, subscript 0 that precedes it, plus our information on our cobalt-59, obviously cobalt element 27, so we show the 27 as the subscript that precedes it, 59 for the particular isotope of cobalt we're interested in. That gives rise to some unknown product along with an alpha particle. So in step 2, we're going to find the mass of that missing, the unknown element that we're creating. So on the left-hand side, we have a 1 for the mass of the neutron, 59 for the mass of the cobalt, so that's a total of 60. On the right-hand side, we already have a mass number of 4 due to the helium nucleus, the alpha particle. So when we subtract that out, we know that the other mass on the right-hand side, the other element that we produce, is going to have a mass number of 56. Step 3, we can find that missing atomic number by looking at the left-hand side. We have 0 plus 27 gives a total of 27 on the left. We already have 2 protons on the right as part of that helium nucleus in the alpha particle, and therefore we need 27 minus 2, which gives us 25 as the missing atomic number. When we look at the periodic table, we find that element 25 is manganese, so that's the symbol of our new nucleus produced. And now we're ready for step 5, our final step, writing that complete balanced nuclear equation. On the left-hand side, we have our 1, 0, N for the neutron, plus the 5927 cobalt, CO for the cobalt, gives rise to 5625 Mn for manganese, plus 42 He to denote the alpha particle. Hopefully writing equations has been fun, because you're going to do a lot more of it in the sense of chemical equations in coming chapters, but here for the nuclear equations, we've had a very logical and reliable method that hopefully you've been able to understand and master, and try the homework set questions, try your end of chapter questions. If you need additional practice, contact me if you're really struggling, but hopefully you'll get yourself in very good shape for whatever happens to be on that exam for chapter 4.